organized and signals to your interviewer that you think in a structured way. Here's the 5-step approach we'll follow today. Step 1. Requirements. We'll define both functional requirements, meaning what the system does, and non-functional requirements, meaning how well it does it. Step 2. Core entities. What data are we actually persisting? A quick high-level list before we get into details. Step 3. API design. What's the contract between the client and the backend? What endpoints do we expose and what do they return? Step 4. High-level design. We build the simplest version of the system that satisfies our functional requirements. No optimization yet, just get it working on paper. Step 5. Deep dives. Now we evolve the design to meet our non-functional requirements one by one. This is where the real interview happens. The most common mistake candidates make is jumping straight to a complex distributed system before they've even agreed on what the system needs to do. Don't do that. Follow the steps. Let's start with functional requirements. The core features of the system. First, a user can submit a long URL and receive a short URL in return. That's the primary feature. Everything else supports it. Second, anyone with a short URL can be redirected to the original long URL. This is the read path, and it's by far the most trafficked operation in the system. Third, optionally, a user can provide a custom alias. Instead of getting a random short code like ABC123, they could request something like /mybrand. We treat this as optional because it's a nice to have, not a core requirement. Fourth, also optional, users can set an expiration time on a link. After a certain date, the short URL becomes invalid. It's worth calling out which requirements are optional because in a real interview, your interviewer might ask you to prioritize. If you're short on time, you focus on the core too and mention the optional ones as extensions. Now, non-functional requirements. These define the quality bar for the system. These are what separate a working prototype from a production-grade design. First, low latency on redirects. We're targeting under 200 milliseconds. Think about it. Every time someone clicks a short link, they're waiting on us before they even see the destination page. Latency here is user visible, so it matters a lot. Second, scale. We need to support 100 million daily active users and store up to 1 billion URLs. These numbers will directly drive our architecture decisions. Third, uniqueness. Every shortcode must map to exactly one URL. Collisions are not acceptable. If two different long URLs map to the same shortcode, one of them becomes unreachable. That's a data integrity failure. Fourth, high availability with eventual consistency. The system should stay up even when components fail. However, we do not need strong read after write consistency. In plain English, if someone creates a short URL, it's okay if it takes a few seconds before every server in the world knows about it. That simplifies our architecture significantly. One quick note, you might be tempted to do back of the envelope math right now. Resist that urge. Only run the numbers when they directly inform a design decision. We'll do that in the deep dives where it actually changes something. Before designing the API, let's think about what data we're storing. This doesn't have to be a full database schema yet, just a high-level list of entities and their key fields. Our first entity is the URL. It needs to store the shortcode, the original long URL, a creation timestamp, and the ID of the user who created it. Optionally, it holds a custom alias and an expiration timestamp. Our second entity is the user. Standard stuff, user ID, email address, hashed password, and maybe a creation timestamp. That's it. 2 entities. The system is not complicated at the data model level. The complexity comes in how we store, retrieve, and scale around these 2 tables. Now let's define the API, the contract between the client and our backend. We need 2 endpoints. The first is a post to /URLs. The client sends the original URL in the request body, along with an optional custom alias and optional expiration time. The server responds with the generated short URL. The second endpoint is a get to /shortcode. The client sends the shortcode in the URL path. The server responds with a redirect to the original URL. Now, and this is a detail that interviewers love, Should that redirect be a 301 or a 302? A 301 means moved permanently. The browser caches this response and will skip your server entirely on future requests to the same short URL. Sounds efficient, but you lose all visibility into your own traffic. No click counts, no analytics, no health signals. A 302 means move temporarily. Every redirect routes back through your server. You can log every click, track analytics, monitor for abuse, and check link health. The slight overhead is completely worth it. We'll use 302. In a production system, observability is not optional. Now for the high-level design. The rule here is start simple, but still draw the full skeleton so your interviewer can see the complete picture. Here's our cast of components: a client, an API gateway, a write service, a read service, a primary database, a Redis cache, Kafka for event streaming, and OpenSearch for full text search and analytics. Let's walk through each flow. The client is the browser or mobile app making requests. It never talks directly to a service. Everything goes through the API gateway first. The API gateway handles routing, authentication, and rate limiting. Short URL creation requests go to the write service. Redirect requests go to the read service. Keeping these two paths separate, even at the gateway level, means we can scale and deploy them independently. Let's trace the URL creation flow. The client sends a post to the API gateway. The gateway routes it to the write service. The write service generates a shortcode. More in the date beasts the deep dives, saves the mapping to the primary database, and publishes a URL created event to Kafka. It then returns the short URL to the client. That Kafka event is consumed by two downstream systems. First, an analytics consumer that tracks creation patterns and usage data. Second, an OpenSearch sync worker that indexes the URL record so users can later search their own short links by keyword or tag. Now the redirect flow. The client requests a shortcode. The API gateway routes it to the read service. The read service first checks Redis. If there's a cache hit, which will be the case for the vast majority of popular links, it returns the long URL immediately and sends back a 302 redirect. No database involved. If there's a cache miss, it queries the primary database, populates Redis, and then redirects. What about expiration? On every redirect, the read service checks the expiration timestamp stored on the URL record. If the link is expired, it returns an HTTP 410 gone. Simple, no cron job needed. This architecture satisfies all four functional requirements and sets us up cleanly for the deep dives. Deep dive 1. Uniqueness. How do we generate short codes that never collide? Let's walk through the options systematically. Option A. Take a prefix of the long URL. For example, the first 6 characters of the domain. This has catastrophically high collision risk. Hundreds of millions of URLs start with HTTPS that all map to the same shortcode. Hard no. Option B. Generate a random number and base62 encode it. This works, but there's a mathematical problem. Due to the birthday paradox, once you have around 880,000 URLs out of a billion, you're likely to see your first collision. Every write would need a database round trip just to verify the code isn't already taken. That adds latency and creates a race condition under high write load. Option C, Mondabot, hash the long URL using MD5 or SHA, then base60 to encode the result. This is deterministic, which means the same long URL always generates the same shortcode, a nice property. But the collision rate is identical to option B. You still need to check the database on every write. Option D, use an auto-incrementing global counter, base62 encoded. The first URL gets counter value 1, the second gets 2, and so on. Since each counter value is unique by definition, there are 0 collisions. No database check needed on writes. This is the winner. Let's talk about base62 for a second. We use 62 characters, digits 0 through 9, uppercase A through Z, and lowercase a through Z. At just 6 characters per shortcode, that gives us 62 to the power of 6, about 56 billion unique combinations. That's more than enough headroom for a very long time. The one legitimate concern with a plain counter is predictability. If your counter is at 1042, a competitor could just iterate through nearby values and enumerate all your links. We fix this with skids, a bijective encoding library that maps your counter to an obfuscated, non-sequential string. The mapping is reversible, collisions are still zero, but the output looks random. Problem solved. Deep Dive 2. Keeping redirect latency under 200 milliseconds at scale. Without any optimization, a redirect means scanning a table of 1 billion rows to find the matching shortcode. That's nowhere near 200 milliseconds. Here's how we fix it in layers. Layer 1. Database indexing. We set the shortcode as the primary key. This automatically creates a B-tree index on that column. B-tree lookups on a primary key are extremely fast. Essentially, constant time for an equality search. This is the single most important optimization, and it costs nothing extra. Just model your schema correctly. Layer 2, Redis, read through cache. Even with indexing, a database read involves disk I/O. At 100,000 requests per second, that adds up fast. We add Redis in front of the database using a read-through LRU strategy on a cache hit, which is the vast majority of requests for popular links. We serve the long URL directly from memory. No disk, no network hop to the database. Sub-millisecond. On a cache miss, we fetch from the database, write to Redis, and redirect. Layer 3, API Gateway Rate Limiting. This isn't just a security feature, it's a latency protection mechanism. Without it, a single bad actor hammering the redirect endpoint can monopolize connection pools and degrade latency for every other user. The API gateway enforces per IP and per token rate limits, rejecting abusive traffic before it ever reaches your services. Layer 4, CDN, optional. For users spread across the globe, even a fast origin server in US East adds latency for someone in Southeast Asia. A CDN caches redirect responses at geographically distributed edge servers. The trade-off: CDN cached responses don't always reach your origin server, so you lose some observability. Worth evaluating based on your traffic geography, but not always necessary. Deep Dive 3. Scaling to 100 million daily active users and 1 billion stored URLs. 100 million users divided by roughly 100,000 seconds in a day gives us about 1,000 requests per second on average. But traffic spikes hard during business hours and viral events. Realistically, we need to handle 10,000 to 100,000 requests per second at peak. A single server handles about 1,000 requests per second. We need horizontal scaling. Let's think about the traffic pattern. Redirects, the red path. Aksa kek count, aknar tetra count for the overwhelming majority of traffic. URL creation from the right path is much rarer. This asymmetry means we scale the read service and write service independently behind the API gateway. The read service runs many instances. The write service runs far fewer. Now the counter problem. If 10 write service instances each maintain their own local counter, they'll produce overlapping IDs and we're back to collisions. We move the counter to Redis and use the atomic incr command. Redis is single-threaded for command execution, so incr is race condition safe by design. To reduce Redis round trips, each write service instance prefetches a batch of 1,000 counter values at startup and increments locally from memory. It only returns to Redis after exhausting its batch. This cuts Redis traffic by a factor of 1,000. Now let's talk about Kafka. Every URL creation event is published to a Kafka topic. We have two consumer groups reading from it. The analytics consumer processes click events in near real time. The OpenSearch sync worker indexes every URL so users can search their links by keyword, domain, or tag. Kafka decouples these consumers from the write service entirely. If OpenSearch falls behind, it doesn't slow down URL creation. For storage, 500 bytes per row times 1 billion rows is roughly 500 gigabytes. That fits on a single modern NVMe SSD. If you do eventually need to shard the database, hash the short code modulo n and route to shard n. Simple, even distribution, no cross-shard queries needed since every lookup is by shortcode. Deep Dive 4. High availability. The goal is to eliminate single points of failure so the system degrades gracefully rather than crashing hard. API gateway, run multiple instances behind a global load balancer. Read and write services, run multiple instances behind a load balancer with health checks and round robin routing. If one instance goes down, the load balancer stops sending traffic to it within seconds. Autoscaling handles traffic spikes automatically. Redis cache. If it becomes unavailable, requests fall through to the database. The system slows down but does not go offline. Redis counter. We run Redis in high availability mode with a primary node and one or more replicas. Redis Sentinel monitors the primary and auto promotes a replica on failure. We also enable Redis persistence, AOF logging, so the counter survives a full node restart. Kafka run a multi-broker cluster with replication factor 3. If one broker goes down, Kafka automatically re-elects a leader for affected partitions. OpenSearch run a multi-node cluster with primary and replica shards. If a node fails, replica shards are promoted automatically. Database run a primary with a synchronous read replica. If the primary fails, the replica is promoted. Take hourly snapshots to S3 for disaster recovery. In a full data center outage, restore from S3 and replay the Kafka topic from the last committed offset to recover any writes that happened after the snapshot. The theme across all of these is graceful degradation. Every component has a fallback. No single failure takes the whole system down. Let's close the loop on everything we set out to build. On the functional side, users can create short URLs, get redirected, use custom aliases, and set expiration times, all four covered. On the non-functional side, low latency via B-tree primary key indexing, Redis, read-through caching, API, gateway, rate limiting, and optional CDN. Scale via microservices, split, horizontal autoscaling, batched Redis counters, Kafka consumer decoupling, and optional database sharding. Uniqueness guaranteed via auto increment counter, base 62 encoding, and skids obfuscation. High availability via load balancing, Redis replication with Sentinel, Kafka multi-broker clustering, OpenSearch multi-node replication, database replicas, and S3 snapshots with Kafka replay for disaster recovery. The components we added, Kafka and OpenSearch, aren't there for show. Kafka decouples the write path from analytics and search indexing, so your URL creation latency doesn't depend on how fast OpenSearch can index. OpenSearch powers the kind of search experience users expect from a production URL management tool. Every decision in this design was made for a reason. We didn't add Redis because caches are cool. We added it because the math showed we needed sub-millisecond read performance at 100,000 requests per second. We didn't add Kafka because event streaming sounds impressive. We added it because we needed to decouple producers from multiple downstream consumers without coupling their latencies together. That's the mindset that separates a good system design answer from a great one. Build for the requirements. Justify every trade-off. If you found this helpful, hit like and subscribe for more system design walkthroughs just like this one. Drop a comment below with the next topic you want covered. See you in the next video.